High-level mathematical reasoning requires the unique ability to resolve extreme visual complexity into a state of pure, orderly logic. Problem 306 illustrates the density of this approach. The nested radicals and stacked exponents are designed to be visually overwhelming at first glance. This level of complexity was the standard for secondary school students in 19th century Russia. The authors, Nikolai Shaposhnikov and Nikolai Valtsov, developed these materials based on their training and teaching experience at institutions like Imperial Moscow University. Their collection remained a staple of mathematical education for over 70 years, eventually reaching 52 editions. In many modern contexts, a math book is treated as a series of tests to verify existing knowledge. Shaposhnikov and Valtsov intended for their problems to serve as an active development tool. The authors designed the book to function as a physical algorithm, building a student's capacity for logic through the sheer volume and sequence of execution. The publisher's note clarifies this intent, describing the book as an instrument for developing mathematical thought, rather than a mere store of exercises. This development relies on a specific structural technique, the cumulative sequence. The book is organized so that techniques introduced in early chapters are repeatedly reused in more demanding, complex settings. We can examine the mechanics of this system by treating the problems in Chapter 9 as an empirical dataset. By tracking the introduction of variables and negative indices, we can map the specific cognitive load the authors demand from the student. This data reflects the rigorous classroom environment of the late 1800s, where disciplined practice was the primary vehicle for learning. By analyzing the structural progression of these equations, we can map how the methodology attempts to transition a student from basic arithmetic to pure literal manipulation. Before the text introduces high-density problems, it establishes a set of foundational rules. These are the primitives. Theorem 1 establishes that the root of a product equals the product of the roots. Theorem 2 applies this to fractions, distributing the root across numerator and denominator. Theorem 3 extracts a power's root by dividing the exponent by the index. Problem 51a puts these rules into immediate practice. The student must use Theorem 2 to decouple the numerator and denominator before further simplification is possible. The system requires the student to ignore intuition and rely exclusively on the application of these strict tools. The visual complexity seen in later chapters is simply the result of these three rules being applied to much larger multivariable expressions. The text directs every expression toward a single terminal state known as normal form. Reaching this state requires a four-step checklist. First, transform the radicand into a single monomial. Second, reduce the root index to its simplest value. Third, extract factors that are perfect powers outside the radical. Finally, remove any irrationality in the denominator. Students are trained to cycle through the primitive theorems recursively until this specific four-step state is achieved. Normal form acts as an anchor. It ensures that no matter how complex the syntax becomes, there is always a clear, predictable objective for the student's mind to follow. To build a student's endurance, the authors utilize a method of cumulative variation. The problems are presented in paired variants. Solving variant A introduces the logic, while variant B requires the same mental operation on different values. The sequence begins with problem 129A, using integers to establish basic mechanics. Soon, problem 131A removes integers entirely, applying the exact same logic to literal variables. By problem 143A, the sequence scales to multivariable expressions and nested roots, maximizing visual density. While the equations look more difficult, the underlying operational requirements are identical to the first numerical problem. This rapid escalation forces students to move past memorizing numerical patterns. They must internalize the rule itself to manage the increasing cognitive load. The most significant transition in this pedagogy occurs when the student moves to imaginary numbers. The text introduces the symbol I with a brief definition. The square root of a negative quantity is expressed as I times its root, and I squared is equal to -1. Instead of teaching a new set of mechanics, the text requires the student to use the familiar normal form algorithm to process these complex numbers. Earlier, in problem 258A, the student learned to rationalize a denominator by multiplying by its conjugate. When they reach problem 399A, they face a complex division. The student applies the same strategy, multiplying by the complex conjugate to remove I from the denominator. The physical process of manipulating the symbols is the same on both sides of the screen. By relying on the established normal form engine, students can accept abstract concepts like complex numbers without needing to learn a new set of behaviors. At this stage, the student's focus has shifted entirely from specific numerical values to the manipulation of abstract symbols. This training reaches its conclusion in Chapter 11, which covers quadratic equations. In this chapter, numerical coefficients have been almost completely removed from the exercises. In problem 14a, the student must solve a quadratic equation composed entirely of literal variables. Success depends on the ability to recognize the structure of the quadratic formula underneath this thicket of variables, placing each component into its correct logical position. The student has progressed from simple arithmetic roots to the total abstraction of the literal quadratic. The Shaposhnikov-Valtsov method succeeds by systematically removing a student's reliance on specific numbers. It forces them to manipulate pure structural logic, the primary requirement for an instrument of mathematical thought.